Yes.
Which packet is the homework packet?
1 second. All right, so questions. Which packet is the which? There's 2 homework packets. There's the quantitative packet. The quantitative packet looks like this. It's a whole series of problems, and there is nowhere near enough space for you to do the problems inside this, which was intentional. And every year, to no avail, students still do the problems inside the interior spacing. I have no idea why. If you don't have it, we got plenty. There it is. That's it.
Oh, this is it?
That's it.
So
This is the quantitative problems. Then there are the free response questions. And I think both of them are contained. So make sure you have both of them. Tomorrow you're going to finish your lab. Questions? Quickly. Today? Today, we march forward. Yep. Any other questions on the reading? Have you guys been doing reading? Reading helps. It will help you understand this class. Yes.
One of the reading questions was about like what are objects thrown up?
Yes.
What is the force?
Yes. Yes. Okay, sure. So, at every point, when you throw an object up, right, what's the net force on this object at every point? Gravity. That's it. That's the net force. Is there any other force acting on this? No. Was there air resistance?
I don't remember. I don't think so.
Even let's suppose there was air resistance. Suppose there was air resistance. If there is air resistance, then when it reaches the top point, what's the net force acting on it? So at every other point in the trajectory, you throw a ball up. Okay? Let's do this. So now let's say the ball's traveling up. What are the forces on it? Gravity and air resistance. Which direction is air resistance? Really? Wait, the ball's going up. Air resistance going down. So here's FFD. So they're both aligned in the same direction. When it's at the top of its trajectory, though, what's the force on it? What force? Wait, gravity. So the force of gravity is on it. What's the force of air resistance when it's at the top of its trajectory? Zero. Why? That's right. So there's no force of air resistance. When it moves down, what happens? So this is at the top. When it's on its way down, what's the net force? Or what are the forces on it? Gravity. Where's gravity acting? Down. What else? Which is acting up. Does that address your question? What was your question? Yes. Yeah, its weight is the force of gravity. Fg is called weight. So that's it. I think then it's just a matter of nomenclature. Fg is the weight of an object. When you ask me, how much do you weigh? What do I say? It depends on. All right, so now let's be a little careful. My weight, my actual weight, is independent of anything except for my mass and the mass of the Earth. That's it. And how far I am from the Earth, or the center of the Earth. We'll find that out later. In other words, my actual weight, my real weight, which is the force of gravity on me, It's totally independent upon whether I'm accelerating or not. What a scale says my weight is depends on whether I'm accelerating or not. Because what a scale tells me is what? What is the scale telling me? It's not telling me my weight. It's telling me the normal force, the force that I exert on the scale. So it's important that you have this distinction in your mind. The force of gravity is only able to be measured if you are not accelerating. And you'll see that's harder than you think. Right now, your weight, this is not going to tell me my weight. Anybody want to venture to guess why? Yes. Okay, which motion? That's right, because I am located on like the 45th degree parallel. Where are we right now? Where's our geographic location? What's our latitude? Well, who's got an idiot phone?
An idiot phone?
Yes.
What is an idiot phone?
It's an iPhone.
Oh, I don't have one of those.
All right. So type in Mendham latitude.
Mendham latitude.
Yes, Siri.
She's checking it. 40.77 degrees north.
All right. So we're 40.77 degrees north of what? The equator. Okay? What you'll find out later is that means that we're actually going to be rotating. As a result of the rotation of the Earth, that's not going to give us our true weight. In order to be at our true weight, we have to be at one of the poles. But let's get ahead of ourselves. So, now we go to the train. Because now this whole lesson is about systems. And this is really the meat of this course. Learning how systems behave. If you're only dealing with single objects, well, life is not that fun. And what this is a pedagogical exercise. It's actually going to show you how Newton's laws kind of work together, how they patch together. So here are these three cars, M1, M2, M3. And let's suppose they're all attached. Well, they are all attached, but let's suppose they're really attached. In other words, we can just look at these like this. Anybody know why I put it on sleds instead of wheels? Yeah, I didn't want to deal with rolling friction. So, in fact, we're not going to be dealing with friction at all. This is a frictionless surface. So there's a number of things that you're going to get out of this. Namely that the net force acting on a body is proportional to its mass. Seems pretty obvious, right? The net force is proportional to the mass. So let's start. So which body do we want to start on? How about we start on M3? Why do we want to start on M3? Well, let's actually do all the free body diagrams in one shot. So, what are the forces acting on M3? Yes? Gravity and normal force and which force? The force from what on what? What body is acting on M3? Correct. So this is the force of 2 on 3. And of course we have the normal force and gravity. And I'm not worried about them. They're there. Trust me, they're there. Here you go. Just to make you happy. Fn3, Fg3. But I'm not worried about them for this exercise. Yes? The train is being pulled with a force F. Or you could say that there is a motor on the front of M1 which is responsible for its locomotion. And there's a force F acting on it. So what do we have here? Well, what's the net force acting on this third car? That's right, F2, 3. And what does that equal to? So the net force on car 3 is equal to what? What M?
Oh, M3.
M3, A3. And what can you say about A3, A2, and A1? That's right. Why?
They're all attached, and since
It's
they're
one.
force, it's a continuous line.
Very good. So, they're all going to have the same accelerations. They're all connected. This is called a constraint. They're all connected. So, naturally, Harrison says, well, how do you know? And what's the answer? You imagine what would happen if they weren't all equal. And if they weren't all equal, what would you observe? They would either crash into one another and compress, or they would split apart. And this is the type of thought experiments you have to do as you're learning this material. So therefore, this is equal to M3 times A. Okay? So now let's do a free body diagram. Let me check something real quick. Oh, okay, but before we do this, what can we do? We can find A in terms of F. Why? Because if you look at this, what is F pulling on?
M1, M2, and M3.
That's right. So we can actually take all this and make it a blob. And F, we do a free body diagram on the blob. And what are the forces acting on the blob? This is called a system. It's just F and the force of gravity and the normal force. So Fn of 1, 2, 3, 1, 2, 3. And this is Fg of 1, 2, 3. And of course, the net force acting on it is F. And so we get, from Newton's second law, it says what? Net force equals the mass times acceleration. Well, what's the mass of this system? This whole thing that's being pulled with F. That's right. So it's M1 plus M2. Well, let me just say MA first. All right? And so the net force is F, and this is M1 plus M2 plus M3 times A. And so then we can find A. A is equal to F over M1 plus M2 plus M3. And so now I'm going to take this A, and notice this A is the A of the system, correct? That A of the system has to equal A of the third car. Why? Because they're all connected. So we plug this in. What do we get? We get M3 times F over M1 plus M2 plus M3. And what do we notice? That the force of 2 on 3, which is the net force on 3, is equal to what? The proportion of the mass of body 3 to the total mass of M1, M2, and M3 times the what force? The total force on the system. So what is this showing you? This is showing you that net force is allocated how? I can't hear you. Proportional to the mass. Net force is allocated in proportion to mass. It's a very, very important point when you're actually going to solve problems quickly. Yes?
I'm kind of confused on what that means.
You'll see. Because guess what we're going to do next? Free body diagram on the second one. So I go to the second one. Maybe I'll do the second one on the board. Unfortunately, it's going to affect the video, but that's why you come to school. We came to school to see you live, Mr. Cleo, not to watch the video. What a joke. So, free body diagram on M2. What are the forces acting on M2? So we have the force of 1 on 2. We don't even care about gravity and normal force for this problem. And what else do you have? Very good. Which way is 3 on 2 directed? Very good. The force of 3 on 2. And how did you get the force of 3 on 2? Because of Newton's third law, exactly. So what's the net force on M2? So the net force on body 2 is equal to M2A2, right? Which is equal to M2A, which is equal to M2 times F over M1 plus M2 plus M3, right? All right, well, that's cool. The net force is acting on body 2 is proportional to the mass of M2 to the total mass times the net force acting on the total system. But now let's actually investigate this a little closer. Because what do you get here? What are the forces acting on body 2? Okay, so it's F of 1 on 2, right? Plus or minus? Minus F of 3 on 2. And that's equal to M2 F over M1 plus M2 plus M3. So what can we get out of this? We can get the contact force of body 1 on body 2, correct? And what do we get? We get the F of 1 on 2 is equal to F of 3 on 2 plus M2F over M1 plus M2 plus M3. But what's F of 3 on 2 equal to? Yes? Very good. This is equal to M3 times F over M1 plus M2 plus M3 plus M2 times F over M1 plus M2 plus M3. But what is this equal to? I can't hear you. Yes? F2 on 3 is equal to F3 on 2, but opposite direction. Notice we took the opposite direction into account where? Where did we take the direction into account? In the free body diagram. So in magnitude, right, this is this. The sign we took into account here. We took that into account here. We carried this over to the other side, but that's just F2 on 3. So what do we get? I can't hear you. What do you get? Quickly. m2 plus m3 times F over m1 plus m2 plus m3. Yes?
So we're finding the forces on M2.
This is the contact force of 1 on 2. Notice that contact force is equal to what? So now I want you to think about what the significance of this is. Talk to each other for a minute. The physical significance of this.
So the contact force isn't the same as the force.
It's not the same as the net force, because the net force is going to be the contact force of this on that and the contact force of this on that. All right, so who has it? What is the physical significance of this? What does F1 on 2 represent? Yes. In other words, I combine the second car and the third car into a blob. What are the forces acting on the blob? What's the force acting on the blob, M2 plus M3? The only force acting on it is F of 1 on 2. So this is the net force acting on a system comprised of M2 plus M3. Notice that net force is what? Proportional to the mass. Now we go to block 1. So we go to block 1. What are the forces on block 1? F? Which way? And what else? F 2 on 1. And what do we have? That F minus F2 on 1 is equal to M1A. So therefore F is equal to F2 on 1 plus M1A, which is equal to, well, we know what this is because we just found it. What is that? So it's M2 plus M3 times F over M1 plus M2 plus M3. And then M1A is M1 times F over M1 plus M2 plus M3. And what do we end up with? Yes? Why is F2 on 1 not negative? Who wants to answer? Yes.
Okay, so on with the first equation where it says F minus F2 on 1, that's where we took into account the direction of it. And that's adding together, like, the directions are taken into account of the problem.
So F1 on 2, right, is equal to negative F2 on 1. But that negative just means it's opposite direction. So another way to just write this is to say that they're equal, right? And where do you take into account the direction? On the diagram. And that's exactly what I'm doing here. Notice, on the diagram, where is F of 2 on 1 directed? That way. Where's F of 1 on 2 directed? that way. So that's why I'm always a little bit hesitant when I introduce Newton's third law to say F of 1 on 2 equals negative F of 2 on 1. Because practically, on a practical level, how do we take into account that minus in the FBD? So what do we end up with here? Yes. F equals F. And you're like, well, that's not interesting, Mr. Khalil. But we're done a proof. We're not done. This isn't some problem with some numeric answer. What you're learning here is that Newton's laws are internally consistent when you're dealing with more than one body. Notice how many bodies did we deal with here? You sure only 3? Be careful. 4? How many bodies did we deal with? First we dealt with this entire thing. Then, so that's 1. Then 2, 3, 4. Then 5. I think 5. Is that it? 5, right? Because it's the entire thing as one body, then each of these individually, and then the last 2, and then we never dealt with these 2 in isolation, right? So it's 5 bodies we dealt with in this problem. And it didn't matter how we actually applied Newton's laws to each of those bodies. It was all internally consistent. So that is what's called a pedagogical exercise. It's to show you how something is internally consistent. Now, let's actually look at an applied problem. So my favorite systems problems are the Atwoods. So which Atwood do you want to take? Table or hanging? Anybody know what I'm talking about? Excellent. So, table Atwood is a very simple setup. You take a pulley, you attach it to the end of a table. Now let's just do the hanging Atwood first. By necessity, we will do the hanging Atwood. Anybody see one of these rods? How often does this happen where I just start randomly searching for something in class? Does this happen in other, science classes? Well, are there demos in other science classes? I'm sure there are. I guess chemistry is always a little bit different because their safety is such an issue that they have to set up in time. They have to do some real prep work. It's almost impossible to do prep work here because other teachers are teaching while I have my periods off. So I'll go and demonstrate the hanging Atwood first. And of course, it doesn't work. Take this. Ah, my God. Who did this? One. All right. Here's a pulley. Is there any Boy Scouts in the room? Excellent. All right, sir. I need your Boy Scout skills, which means you need to tie a knot. Pressure is on. I think. Well, no. There you go. I think I got this actually. I'm not as useless as I usually am. I say that and then all right, so here's an Atwood. As you can see, what do you have? No. And the answer is nothing, Mr. Cleo. And the answer is why is there, or the question is why is there nothing happening? And you take a very careful observation, you notice that they both have the same mass. So let me create an imbalance. And notice, when there's a mass imbalance, what does it do? It starts accelerating. That's right. And so what the Atwood machine does is it provides a means of actually limiting the acceleration of gravity. You can create an elevator out of this. Oh, you weren't supposed to hit each other. You're not behaving well. So let's see. And there you go. Now, granted, this would be a pretty dangerous elevator because there's no stopping mechanism. I guess it'd be pretty easy to make a stopping mechanism. So let's take a look at the Atwood machine, because you'll get a real feel for how systems behave when you look at this closely. So, and if you're looking for numbers, I'm going to break it to you real hard, the hard way. There's going to be no numbers. Everything's going to be algebraic. So, what does this look like? Here's a pulley. Here's a mass. Here's another mass. Call this M1. Call this M2. Guess what you do? Free body diagram. Which body? M1. Forces on M1 are gravity and what else? I can't hear you. Tension is correct. No. 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 M2. Who we got? What else? Tension. That's correct. What about the second one? That's right. All right. Now, we need to actually make sure our coordinate system is inertial. So how are we going to do this? Well, a couple of things. What can you say about these two tensions? Are they equal? And the answer is, well, it depends. So let me actually start giving you assumptions, and you'll see why later. Maybe I'll even do this problem in the middle of this problem. So, string is massless. Pulley is massless. You'll see why at the end of this problem. I'll show you why that assumption is necessary. You'll see why this assumption is necessary in Unit 6. But these two combined, actually, can anyone speculate why the pulley being massless is important? Anyone? Yes.
Because if it had a mass, then there'd be some force of gravity acting on the pulley.
No, because that pulley has a pin in the middle, and that pin exerts a force, basically a normal force equal to the weight of the yes. It's about rotational energy, correct. If that thing had mass, when it rotated, it would have rotational energy. How do you know that? How do you know it? At the end of the day, physics is about feeling. It's about feelings, guys. All right? Physics is about feelings. All right? So if you see something metal and it's rotating fast, what do you not do? That's right. You don't jump on it. You don't touch it. Why don't you touch it? Because if you touched it, you would get burnt. What's that telling you? It has energy. That's right. It has energy. But if that thing that is rolling is massless and you touched it, it's all good. Come on now, guys. You guys are a tough crowd. So, that was a joke that just, whatever. Anyhow. So, now let's think about M1 and M2. What can you say about the acceleration of M1 and the acceleration of M2? They should be opposite and equal. So we'll say A1 equals negative A2. Why? Yes.
They're going in opposite directions.
That's right. And they are?
Equal in
They are, what are they, these two masses are? It starts with a C. Connected. They're connected. What would happen if the magnitudes of the accelerations weren't the same? What would you observe? So it would be instead of a string, it would be a spring. That's right. If it was a spring, then all bets are off. But luckily, there's no P in string. There's no P in string. Meaning if there was a P in string, it would be a spring. All right? Oh, man, you guys are a tough crowd. It's way too late in the day for these jokes. All right. So, we got the free body diagram. We've got how the system's connected. Now we need to solve Newton's second law. So the consequence of this and this implies that Ft1 equals Ft2. And both of them are equal to Ft. I'll explain this one. I already gave you a quasi-explanation for this. But you'll see why the string being massless is important shortly. So now let's begin solving. So we write Newton's second law for each body. So for body 1, what do we have? Which way do you want to call up? So we'll call up positive, and we'll call down negative. So then on body 1, what do we have? What does Newton's second law says? Net force equals M1A1. And so what are the net forces? What are the forces on it? Ft minus Fg1 equals M1A1. What about on body 2? M2A2, which is M2 times negative A1. Guess what I'm going to do with these two? How? Subtract is correct. So let's subtract these two. What do you get? I can't hear you. It's going to take you about 30, 40 seconds minimum. Unless you've got a really astute mind. Subtract. Bottom from the top. What do you get? Yes? Come on. Subtract this. What happens to the FTs? They cancel. What do you get? Minus Fg2 is Fg2. Right? Plus negative Fg1 equals M1A1 minus M2 negative A1, which is plus if you want, I could even say minus negative Fg2 plus negative Fg1, just so that everything's consistent. You see the exact algebra that I'm doing. You get Fg2 minus Fg1 is equal to what? Yes. Guys, you're going to need to do this on an exam in under 15 minutes.
So we're just doing Fg2 minus Fg1.
What do you get on this side?
M1A1 plus M2A1.
So it's M1 plus M2 times A1. So what do we have? Well, what's Fg2? What's Fg2? I can't hear you. We have Fg2 minus Fg1 equals M1 plus M2 A1. What's Fg2? If I say the force of gravity of an object, you say mg. When I say Fg, you say mg. So what's Fg2? M2g. What's Fg1? M1g. So we get A1 is equal to M2 minus M1 g over M1 plus M2. Notice, if M1 equaled M2, what's the acceleration? That's right. If M1 equals M2, A1 is 0. Does that make sense? Yeah, it should. What's the maximum value that A1 can have? Why? How'd you get that? Okay, but give me a physical explanation. Give me physically what the sequence would be to show that. Let M2 be much, much greater than M1. If M2 was much, much greater than M1, what would happen? The numerator, this thing in the parentheses, would be approximately equal to what? What would the numerator approximately equal? If M2 is much, much greater than M1. M2, what would the denominator equal? M2. Notice M2 over M2 is 1 times g. So the maximum value, the maximum acceleration it can have is that of gravity. The minimum is clearly 0. At least in magnitude. What about A2? What can we say about A2? A2 equals negative A1. So therefore we would say A2 is equal to M1 minus M2 times G over M1 plus M2. Yet again, I'll say this and I'll say this again. If you're looking for a formula, you're looking in the wrong place. All I have to do is modify this slightly. Formula is worthless. Now what? Now let's solve for the tension. How do we solve for the tension? We're going to need to plug it in here. We have Ft minus Fg1 is equal to M1A1. And we have A1, correct? So Ft is equal to Fg1 plus M1A1, which is M1G plus M1. What's A1 equal to? Guess what I'm going to need to do? Common denominator. What's going to be the common denominator here? M1 plus M2. So we have Ft equals M1G times M1 plus M2 over M1 plus M2 plus M1 times M2 minus M1 times G over M1 plus M2. Now what? Ft is equal to, start multiplying this out. We have our common denominator. What's our common denominator? M1 plus M2. Start multiplying. What do you get here? Yes. Let's FOIL this. M1 squared G plus M1 M2G plus M1 M2G minus M1 squared G, all divided by the common denominator of M1 plus M2. So therefore, Ft is equal to Does this make sense, yes or no? Yes. Why? Notice I didn't say whether my algebra makes sense. Now I'm asking you a physical question. Does this physically make sense? Yes or no? Yes.
Well, I don't really know the answer to the last question, but since M1 and oh wait, never mind. That's not.
Let's think this through. So, if you're looking at this, and this is a little tricky. It's a little bit tricky. If I'm holding, does this physically make sense? Is there a way to physically rationalize this? Well, what happens if M1 is very small and M2 is very large, or M2 is much, much greater than M1? Yes.
Get 2G over M2, which would give us 2G.
Would give you 2G. And so what would that imply? See, does that make sense? 2G. The force of tension would be twice that of gravity. And the answer is that should make sense because you'll see that this will make a lot more sense when I do the table Atwood. So maybe I'll hold off on asking the reasonability of this. But this formula is correct. You'll see how reasonable it is when we get to the table Atwood. The table Atwood is the track and the hanging mass. So, any questions on this first? So now, why massless strings? Why massless strings? Yes?
Would it be because if the strings have mass, then when the pulley goes like this, the mass of this side would be greater
Okay.
than it was before?
Well, that that would just tell you that you'd have to account for it. The question is, why does massless strings imply the force of tension is the same? So let's see. Let's suppose that you have a block, and that block you're pulling with some force of tension. Excuse me, you're applying some force, some applied force here. And call this big M. And let's say this rope has a mass of little m. So now, what force, let's actually do a free body diagram on this. You're applying a force of tension here, correct? So that force of tension is going to be a net force acting on this thing, correct? So you have Ft is the net force, and that's equal to the mass of this whole thing times A, correct? What's the mass of this whole thing? Big M. So M plus big M times little a. And so therefore A, we can say that A is equal to Ft over little m plus big M. So now I want to actually look at this box. So what are the forces acting on the box, this big box? Anyone? Yes. Gravity and normal force, but even whatever. We're doing this in deep space. This is an experiment we're doing in deep space. So in other words, what force is that going to be? What type of force? Some tension force. So call this Ft2. Notice what I'm going to show here is what happens when little m goes to 0. In other words, this mass, this rope has a mass m. So I'm not going to speculate whether Ft equals Ft2. I'm going to assume that they're not equal. So what's the net force acting on? What is the net force acting on big M? Be careful. What's acting on big M? Just Ft2. So we have Ft2 is equal to big M times right? But what can you say about that rope in that box? They are, what's the word? Starts with C. Connected. So therefore, they're going to have the same acceleration. So this is equal to big M over little m plus big M times Ft. So what do you notice here? If little m equals 0, then Ft2 equals and there you go. There's your proof. In other words, you assume the very fact that the string is massless tells you that the tension is uniform along the string. And as you can see, which is going to be greater, Ft2 or Ft1? Or Ft2 or Ft? Which is greater of the two? You sure? Ft is greater. Why? What can you say about this ratio? What can you say about this ratio? Yes. Correct. This ratio is less than 1. And it's only equal to 1 when little m is 0. Any questions? This is a really good time to ask questions. Because you're seeing a lot of important theoretical things going on here. Why massless strings? Why? Because if it had mass, what would happen? The force of tension would decline along the string. Why must the force of tension decline? How would you physically interpret this? Why, when I pull on a heavy string, is the force of tension less here than here? Because some of this force was allocated to do what? Accelerate that mass. Because I'm getting a lot of blank looks. This is the time to ask questions. All right. So, how much time we got? 3 minutes? All right. So what I want you guys to do is start thinking about the table Atwood. Free body diagram. Here's the table Atwood. Let there be friction. Where would friction act on? Which one? M2. Free body diagram it. I will be here after school to answer questions as well. Everything. You're going to need everything here. And the reason you need everything is because I said, what's present? Friction. And so why is the normal force important for that? It's proportional. That's right. That's another great question. You're assuming that I'm going to answer that question. So maybe you should consider both cases. Because if it was at rest, what was that telling you? What's acting on the system? Static friction. If it's in motion, then it's kinetic friction. Very good. Very, very good. Yes? No, not air resistance. Air resistance is too complex for this class. You need calculus. And as you can see, the algebra in this class is a lot more intense than the algebra class that you took. This is a class where you will really learn algebra.